Okay, so let's see what happens with complex eigenvalues. Remember, for real eigenvalues, it just depends on if the real eigenvalues are positive, you get a growing solution. If there was a negative eigenvalue, you get a decaying solution. And what happens with the complex case? Well, here's a matrix that we've got to work out the characteristic equation. You can do it in Mathematica or MATLAB if you want. But the thing is, it's arranged so that if you think of the quadratic equation, b squared minus 4ac is negative. So we get negative things in the square root, and we end up with complex answers. And that's because of that minus 20. You put in those complex roots, find their complex eigenvectors p, and then see what happens as t changes, and in this case here's x1 and x2 plotted as a function of time, and what we get is something that's rotating, and that's associated with complex eigenvalues. So generally something that's oscillating, in this case oscillating and getting bigger as well, tends to be associated with complex eigenvalues. So far, so we used our eigenvalues now, and we've used them to compute powers of A. We've solved linear systems of differential equations, and the key is to do it by diagonalizing, which is called decoupling in the sense of engineering.